Yellowstone National Park could be sitting on a time bomb. There is a supervolcano underneath the national treasure that's more than twice the size of the park itself.
There have been some epically big eruptions, and some of them not so long in the geologic past.
Yellowstone National Park, once serene, is now a focus of concern as recent reports show over 1,000 small earthquakes. These continuous tremors, including a record-breaking one, stir fears of a potential catastrophic eruption. Are these signs of an imminent disaster? Join us as we probe the escalating seismic activity threatening the park. Yellowstone's rising seismic dilemma. The U.S. Geological Survey's recent earthquake report showed a big increase in small earthquakes, with over 1,000 minor quakes detected in the park last month alone. This included the largest earthquake ever recorded in the Rocky Mountains, which happened just west of Yellowstone. This peaceful park, known for its geysers and green landscapes, is now surrounded by worry and uncertainty. The recent findings have worried the local community, raising fears of possible danger. The unsettling news came after a strong earthquake shook Yellowstone Lake, initially thought to be a minor tremor. But this was just the start of a series of shocks that would soon reveal a much bigger threat. Just 2 days after the first disturbance, the park experienced hundreds of earthquakes, alarming residents and scientists. The continuous seismic activity has raised concerns about the possibility of a massive eruption that could have devastating effects, not just locally, but across the continent. In 2020, Yellowstone was the center of a significant seismic event when the area had a series of tremors, mostly southwest of Yellowstone Lake, between Heart Lake and West Thumb. These tremors were notable for their frequency and strength. Michael Poland, the scientist in charge of the Yellowstone Volcano Observatory, shared via email that while the swarm was large, it wasn't unheard of. He remembered a similar event from June to September 2017, which included over 2,400 tremors, the strongest being a 4.4 magnitude quake. Adding to the natural seismic activity, there were also artificial tremors created by a vibroseis truck, part of a research project by the University of Utah and the University of New Mexico. This truck, weighing up to 70,000 pounds, moved through important park areas like Old Faithful and West Thumb, shaking steel plates against the ground to send low-frequency energy waves. This helps create detailed images of the top layers of Yellowstone's magma chamber, often called a supervolcano. Despite the swarm of earthquakes and experiments, the USGS Volcano Hazards Program kept the alert level normal as of September 1st. Scientists continue to reassure the public that most earthquakes in Yellowstone are too small to be felt, but are carefully monitored by advanced seismic equipment throughout the park. This ongoing monitoring is part of a larger effort that became more intense after the 1959 Hebgen Lake earthquake, which happened near the park's western edge. This historic quake sparked a strong interest in understanding and tracking the seismic details of Yellowstone, a region admired for its beauty and respected for its active geology. On the night of August 17th, at exactly 11:37 p.m., a huge earthquake with a magnitude of 7.3 hit. It was the strongest earthquake to ever strike the Intermountain West. This terrible event caused the deaths of 28 people and caused a lot of damage to Yellowstone National Park, especially its famous hydrothermal sites, including Old Faithful Geyser. The earthquake's force caused a massive landslide in Madison Canyon, sending about 50 million cubic yards of rock and debris into the area. This huge amount of earth created a natural dam on the Madison River, forming what we now call Earthquake Lake. Along with this major landslide, many smaller ones happened all over Yellowstone, blocking important roads and damaging buildings and structures. After this destruction, scientists realized the urgent need to improve the way we monitor earthquakes in and around Yellowstone. This led to a big increase in money spent to enhance the geophysical monitoring systems in the area. Now, state-of-the-art seismometers are continuously keeping track of the park's active geological environment. Looking at Yellowstone's history with earthquakes, the largest one recorded inside the park, was a magnitude 6.1 event in 1975, near the Norris Geyser Basin. There have also been several significant earthquakes in the magnitude 5 range, 29 in the magnitude 4 range, and 379 in the magnitude 3 range. The most recent significant earthquake happened on June 15, 2017. This 4.4 magnitude quake was part of the Maple Creek Swarm, a series of over 2,300 earthquakes that shook Yellowstone from June to September that year. Over 120 residents in Yellowstone and nearby areas, including the town of West Yellowstone, Montana, felt this particular quake. Earthquake swarms, which make up about half of all seismic activity in Yellowstone, are especially important. These swarms usually happen in an east-west band between Hebgen Lake and the Norris Geyser Basin. While most of these swarms are small, having 10 to 20 earthquakes and lasting only a day or two, sometimes a bigger swarm occurs, giving scientists important clues about the seismic activity in the area. By studying data from these swarms, scientists can learn more about what is happening beneath Yellowstone's surface. These swarms not only offer insights into the park's geological behavior, but also help predict possible future earthquakes. As we continue to explore these phenomena, the term supervolcano becomes important. This term describes volcanic fields capable of huge eruptions. The Yellowstone supervolcano refers to the volcanic field that produced the last 3 massive eruptions, as well as a smaller eruption that formed the west thumb of Yellowstone Lake, around 174,000 years ago. Next, let's look at the big eruptions that shaped Yellowstone long ago. Eruptions through the ages. With its deep hot spots, the Yellowstone supervolcano has caused massive volcanic eruptions around 2.1 million, 1.3 million, and about 640,000 years ago. These eruptions created the Island Park caldera, Henry's Fork caldera, and Yellowstone caldera. The eruption 2.1 million years ago at the Island Park caldera was especially fierce, releasing the Huckleberry Ridge tuff. This eruption spewed out ash about 2,500 times more than the 1980 Mount Street, Helen's eruption. The biggest eruption after this formed the Yellowstone caldera around 640,000 years ago, producing the Lava Creek tuff. The eruption at Henry's Fork caldera, happening 1.3 million years ago, created the smaller Mesa Falls tuff and is the only caldera from the Snake River Plain still visible today. The Huckleberry Ridge eruption was a huge event that changed the ancient landscape with its explosive power. It started when the magma chamber released built-up pressure, shooting a massive plume of ash, gas, and molten rock into the sky. This explosion ejected about 2,450 cubic kilometers of material, forming a giant caldera over 50 miles wide. The eruption had global effects, sending ash and gas into the atmosphere that blocked sunlight, causing temperatures to drop and leading to widespread climate changes. Around 1.3 million years later, the Mesa Falls eruption hit Yellowstone again, releasing 280 cubic kilometers of volcanic material and forming a caldera over 30 miles wide. The eruption's pyroclastic flows, superheated avalanches of rock and debris, rushed down the slopes, burying landscapes under thick layers of ash and drastically changing the region's shape. The ash cloud from this eruption rose high into the stratosphere, affecting global weather patterns and causing environmental upheaval. But this wasn't the end of Yellowstone's dramatic past. Another monumental eruption happened about 630,000 years ago, releasing an enormous 1,000 cubic kilometers of material. This event created a caldera measuring 45 miles across, reshaping the land and causing a long volcanic winter. The ash and debris from the eruption blocked sunlight, leading to significant climate changes worldwide. Despite some confusion, Yellowstone is indeed an active volcanic system. The presence of magma beneath the caldera shows ongoing volcanic activity. While Yellowstone might seem different from a regular volcano, the scale and potential impact of a supervolcano eruption are significant and dangerous. Beneath Yellowstone, there is a huge plume of magma held in check by immense pressure. If this pressure is released, the dissolved gases in the magma could bubble out, causing the magma to expand quickly, which could lead to an eruption. Recent studies show this magma chamber is massive, about 80 kilometers long and 20 kilometers wide, holding around 4,000 cubic kilometers of material. However, only 6 to 8% of that is molten rock, suggesting it might not be ready for another catastrophic eruption anytime soon. The deeper reservoir is made of basalt, a low silica rock type that extends far below the surface. New research from Arizona State University has added a twist to our understanding of this system. They found that the magma chamber could change rapidly with new magma entering the system, suggesting that Yellowstone's magma reservoir could potentially reach critical eruptive conditions within just decades. This discovery has raised concerns and highlighted the need for continuous monitoring and research to better understand this powerful volcanic system. The origins of the Yellowstone hotspot have been a hot topic among scientists for a long time. Some believe it's caused by the interactions between the Earth's crust and the movements in the upper mantle. Others think it comes from deep within the Earth as a mantle plume. A big point of debate is its sudden appearance in geological records. At the same time, the Columbia basalt flows in the same area have sparked ideas about a possible shared origin. As the Yellowstone hotspot moved east and north, the disturbances in Columbia followed a similar path before becoming less active. In 2018, a new theory challenged the old view that a mantle plume was responsible. This new idea suggests that volcanic activity at Yellowstone might be caused by movements in the lower mantle, started by water-rich fragments of the Farallon plate descending from the Cascadia subduction zone and breaking off. Those who doubt the mantle plume theory argue that the sinking Farallon plate acts like a thermal shield, breaking up and spreading out the upward flow from the plume. They suggest that any heat reaching the surface from the plume is limited, casting doubt on its role as the main driver of Yellowstone's volcanic activity. These competing theories, from interactions at the Earth's crust level to deep-seated mantle plumes and lower mantle movements, show the ongoing efforts to understand the complex geological processes shaping Yellowstone's volcanic history. As research continues, new findings and evidence keep updating our understanding of this complex geological phenomenon. In light of the potential for a catastrophic eruption, scientists and policymakers are actively looking for ways to stabilize the Yellowstone volcanic system. The challenges are huge, but the possible consequences of doing nothing are even greater, prompting bold and proactive strategies. At the forefront of these efforts is the push to improve monitoring and early warning systems. Research teams are enhancing the network of seismic, GPS, and other advanced sensors across Yellowstone. This improved network helps detect even the smallest changes in volcanic activity, giving crucial time to alert the public and start emergency protocols. Some experts are also considering more direct methods to stabilize the volcanic system. They are looking into techniques to cool and solidify the magma, like injecting cryogenic fluids. This approach aims to physically stabilize the volcanic system, although the scale and logistics of such an operation are daunting. Now, let's see how scientists are trying to lower the risks from this powerful volcano. Innovative tactics against Yellowstone's heat. Scientists are trying new methods to cool down and solidify the magma beneath Yellowstone, a supervolcano. They are using extremely cold fluids, like liquid nitrogen or liquid carbon dioxide, to lower the temperature of both the magma and the surrounding rocks. The idea is that supervolcanoes like Yellowstone are huge and dangerous because they can release a lot of heat and potentially cause massive eruptions. These eruptions could send large amounts of ash, gases, and volcanic material into the air, affecting climate and ecosystems worldwide. By cooling the magma chambers, researchers hope to solidify the magma and decrease the pressure that builds up inside. This pressure can lead to explosive eruptions. To cool the magma, They plan to drill deep into the volcano and inject these cold fluids directly into the magma chamber or the surrounding rocks. These super cold fluids would absorb the heat from the magma, gradually bringing its temperature down. Over time, this could slow down or completely stop the buildup of volatile gases and make the magma thicker, making it less likely to explode violently. The success of this cooling technique depends on many factors, like choosing the right places to inject the fluids and understanding how the cooled magma will behave. Advanced geological models and imaging techniques are essential for finding the best injection spots and for figuring out how the magma might react when it cools. Handling this process carefully is crucial to avoid causing unexpected problems, such as creating cracks in the surrounding rocks or making the magma chamber unstable. That's why scientists are focused on thorough risk assessments and continuous monitoring during the cooling efforts, aiming to reduce the volcanic threat without making it worse. One of the major hurdles is the sheer scale and time required for such an intervention. Cooling a supervolcano like Yellowstone to the point where it no longer presents a serious eruption risk is a massive, long-term project. The enormous amount of magma and the large size of the magma chamber mean that any strategy must be sustained over many decades or even centuries. Additionally, the practicality of pumping cryogenic fluids into such a large system needs to be thoroughly tested in lab settings and through controlled field experiments. These experiments give researchers a better understanding of how extremely cold fluids interact with magma in controlled settings, helping us see what might happen if these methods were used on a larger scale. There are also ethical questions to consider. Changing natural geological processes on a big scale raises concerns about the environmental impact, whether people agree with these actions, and the unexpected outcomes of altering volcanic systems. Scientists and policymakers need to have open and inclusive conversations to balance the benefits of reducing volcanic risks with the ethical and environmental costs of interfering with nature. Using cryogenic fluids to cool and solidify magma is a new idea for tackling the dangers of supervolcanoes like Yellowstone, but it is still in the experimental phase. Turning this idea into a practical solution involves navigating a maze of scientific, technical, and ethical challenges. However, continuous advancements in geology and engineering offer hope for creating new ways to handle the big challenges posed by supervolcanoes. NASA scientists, when thinking about how to cool down a supervolcano, suggested a simple idea: increasing the amount of water in Yellowstone to draw out the immense heat it generates, which is like 6 industrial power plants. Right now, 60 to 70% of this heat escapes into the atmosphere through water seeping into the magma. The rest builds up in the magma, dissolving gases and surrounding rocks, pushing the system towards a critical point where an explosive eruption could occur. NASA's bold plan involves drilling up to 10 kilometers into the supervolcano and pumping water down at high pressure. This water would then return at about 350 degrees Celsius, gradually extracting heat day by day. However, drilling into a supervolcano carries big risks, especially the potential of actually causing the eruption it aims to prevent. The main worry is that cooling the magma chamber from the top could make the overlying rock cap brittle and prone to breaking, possibly releasing harmful gases from the magma that would otherwise stay trapped. This cooling method would only decrease the temperature by about 1 meter per year, meaning it would take tens of thousands of years for the magma chamber to cool completely. While the chamber wouldn't need to be fully frozen to reduce the eruption risk, making it safe could take centuries, if it works at all. Given the unpredictable nature of Yellowstone's complex system, it's hard to predict the outcomes of such an intervention. Most volcanologists and authorities remain skeptical about drilling into Yellowstone, believing the risks outweigh the benefits with our current technology and understanding. Instead, the focus remains on improving monitoring, enhancing emergency preparedness, and continuing to understand Yellowstone's dynamics better. While drilling is a theoretical option, it is not seen as a practical or responsible strategy for managing the risks associated with the volcano. The challenges also extend to predicting when Yellowstone's supervolcano might erupt. Its magma system, lying deep below the surface, consists of a complex network of interconnected magma chambers, reservoirs, and pathways that are difficult to fully understand and predict. The lack of historical data from the long intervals between massive eruptions, such as the three major ones that occurred in the past 2.1 million years, makes it hard to identify reliable warning signs and eruption timelines. Each eruption might show unique characteristics, making it harder to establish consistent patterns. Scientists use various techniques to monitor changes in Yellowstone's system, such as measuring seismic activity, ground deformation, gas emissions, and hydrothermal activity. However, interpreting these data can be challenging, and linking specific monitoring results to an impending eruption is full of uncertainties. The process by which magma rises from the deeper reservoir to the surface, causing an eruption, involves multiple factors like the thickness of the magma, the permeability of the overlying rock, and the buildup of gas pressure, all of which make predictions difficult. The awakening of a slumbering giant. Mount St. Helens usually has about 11 minor earthquakes a week. However, recently, there have been around 35 earthquakes each week. The U.S. Geological Survey says this is because magma is moving under the volcano, causing these quakes. This increase in activity suggests that an eruption might be coming. Since February, there have been 1,368 small earthquakes at Mount St. Helens. Most of these were too small to feel and happened about 3.5 miles below the surface. The biggest earthquake was a magnitude 2 in May. In early June, there was a peak of 38 earthquakes in 1 week. The U.S. Geological Survey believes this could mean the volcano is recharging with more magma. The risk of eruption has gone up. Mount St. Helens is an active volcano in Skamania County, Washington, part of the Pacific Northwest. It's named after Aline Fitzherbert, a friend of explorer George Vancouver, who surveyed the area in the late 1700s. Mount St. Helens is part of the Cascade Volcanic Arc and is about 34 miles west of Mount Adams. It's often called a sibling to nearby volcanic peaks, like Mount Rainier and Mount Hood. Mount St. Helens is relatively young, geologically speaking, having formed over the past 40,000 years. Before its 1980 eruption, the summit had formed about 2,200 years ago. Among the Cascade volcanoes, Mount St. Helens is the most active, especially in the past 10,000 years. Imagine looking at what used to be the 5th highest peak in Washington, often compared to Mount Fuji in Japan, earning it the nickname Fuji-san of America for its symmetry and snow and ice cap. Before the eruption, it stood 5,000 feet above its base, with slopes blending into nearby ridges. The mountain was 6 miles wide at its base and about 4 miles wide at the tree line. The mountain's ice cap had 11 named glaciers. After the eruption, only fragments of these glaciers showed signs of reactivation. Streams from Mount St. Helens feed 3 major rivers: the Toll River to the north and northwest, the Cal River to the west, and the Lewis River to the south and east. These streams get a lot of water from the mountain's heavy rainfall and snowfall, with an average annual precipitation of 140 inches. Stretching up to 16 miles, the Lewis River is key for hydroelectric power. Third-generation dams use the river's flow from the southern and eastern sides of the volcano, feeding into the Swift Reservoir just south of the peak. Now, let's talk about an interesting glacial crater that formed in the winter of 1980 to 1981. This ice giant, known initially as the Tullet Glacier, started growing in the shady parts of the crater walls. Heavy snowfall and frequent avalanches helped it grow quickly, adding about 14 feet of ice every year by 2004. By late summer, the glacier, covering around 0.36 square miles, was split into western and eastern sections by a volcanic dome. The ice often looked dark because of rockfall from the crater walls and ash from volcanic eruptions since 2006. The glacier had an average thickness of 300 feet, with some parts reaching up to 650 feet deep. This made it as thick as the older and larger Carbon Glacier on Mount Rainier. Amazingly, all this ice formed since 1980, making the crater glacier quite young in geological terms. Mount St. Helens has more stories to tell, and the surprises aren't over yet. Awakening the frozen giant. But here's the kicker. In terms of total volume, it's roughly equal to all the glaciers in the area before 1980 combined. Starting in 2004, volcanic activity began changing the glacier. The lobes of ice were pushed aside, and new volcanic domes formed. This turned the glacier's surface into a chaotic mix of ice cascades, crevasses, and seracs because of the moving crater floor. The new domes almost split the crater glacier into two parts. Despite the volcanic activity, the glaciers kept moving forward. The western lobe moved a bit, while the more shaded eastern lobe advanced more significantly. By late May 2008, the two lobes had rejoined, circling the lava domes completely. Since 2004, new glaciers have also formed on the crater walls above the crater glacier, adding more rock and ice to its surface. Mount St. Helens is part of the Cascades Volcanic Province, an area that stretches from southwestern British Columbia to northern California, following the Pacific coast. This area is interesting because of a process called subduction, where a dense oceanic plate sinks under the North American plate. But that's not all. Imagine the oceanic slab sinking deep into the earth. High temperatures and pressures cause water in the minerals to escape. This hot water rises into the mantle above, leading to the melting of new magma. The magma then moves up through the crust, finding its way through cracks and faults, even melting some of the surrounding rock. As the magma rises, it slightly changes the chemical makeup of the crust. Some of this melt eventually erupts on the surface, forming the Cascades Volcanic Arc, which includes Mount St. Helens. Under Mount St. Helens, magma collects in two chambers. The upper chamber is 3 to 7 miles below the surface, while the lower one is 7 to 25 miles down. This lower chamber might even be linked to Mount Adams in the Indian Heaven volcanic field. Mount St. Helens' early eruptions happened in stages. The Ape Canyon stage around 40,000 to 35,000 years ago, the Cougar stage around 20,000 to 18,000 years ago, and the Swift Creek stage from about 13,000 to 8,000 years ago. The current period started around 2500 BC. Spirit Lake is famous for showing the early stages of volcanic activity, which we now call the ancestral stages. These stages are interesting because they show different types of lava compared to today. Back then, the lava was a mix of dacite and andesite. Today we see a broader range from olivine basalt to andesite. Mount St. Helens started growing around 37,600 years ago during a time called the Pine Epoch. The first phase, called the Monkey Canyon stage, had explosive eruptions of dacite and andesite, throwing out hot debris. About 36,000 years ago, a huge mudflow came down from the volcano, showing how powerful these mudflows could be. But that wasn't the worst part. Around 35,000 years ago, the Monkey Canyon stage ended, and the volcano had 17,000 years of relative quiet. During this time, glaciers slowly wore away parts of the ancient cone. Then, about 20,000 years ago, the pumice stage began. It lasted for 2,000 years and saw hot pyroclastic flows and ash, along with growing volcanic domes. The mountain wakes up again, bringing old stories and new warnings, the untold chronicles of Swift Creek. After this, the volcano rested again for about 5,000 years, until the Swift Creek period began. This period saw pyroclastic flows, dome growth, and lots of tephra deposits. It ended around 8,000 years ago, followed by 4,000 more years of calm. Then, around 2500 BC, the Smith Creek eruption phase began with big eruptions that spread ash over thousands of square miles. This period saw one of the largest eruptions around 1900 BC, sending debris far and wide. But that wasn't the most surprising part. By around 1600 BC, this phase left deposits up to 18 inches deep, even 50 miles away, reaching places like Mount Rainier and Banff National Park in Alberta. This phase released about 2.5 cubic miles of material before another 400 years of quiet followed. Around 1200 BC, the Pine Creek period began, lasting until 800 BC. This time had smaller but still powerful eruptions with dense, hot pyroclastic flows settling in nearby valleys. One major event during this time was a large mud flow that partially filled 40 miles of the Lewis River Valley between 1000 BC and 500 BC. Then came the Castle Creek period around 400 BC, which saw a change in the volcano's lava to olivine and basalt. During this time, the summit cones before the 1980 eruption began to form with broken and crushed lavas. A significant lava flow around 100 BC stretched into the Lewis and Columbia River valleys. Another well-known flow, Basalt Cave, with its complex lava tubes, extended up to 9 miles from its vents. These flows carried debris 30 miles down the Towel and Kalama River valleys, possibly reaching the Columbia River. After this dynamic period, another 400 years of quiet led to the brief but notable Sugar Bowl eruptive period, a unique chapter in Mount St. Helens's history. A volcano had a small explosion, which people realized happened before the big eruptions in 1980. Shortly after, it started to erupt softly, forming a small hill. This eruption quickly escalated into 2 loud explosions, throwing out a bit of ash. This event led to layers of ash, hot ash flows, and mudslides, indicating a period of intense geological activity. They observed a new small hill made of special rocks on the east side of the volcano, probably from older times. This hill formed after a significant blast about 700 years ago. Calm periods ended around 1480 with a huge eruption that threw out light gray ash and stones, marking the start of a known old period. This eruption was bigger than the one in May 1980. However, that wasn't the worst part. In 1482, another massive eruption occurred, similar in size to the 1980 event, sending ash and stones up to 6 miles northeast. The ash spread over 50 miles, blanketing the ground with 2 inches of ash. This caused hot volcanic water and mud to rush down the western side of the volcano towards the Kalama River Valley. Over the next 150 years, eruptions created less siliceous lava, forming layers of andesitic ash with light and dark andesite blocks. Lava flowed from the summit crater down the southeastern flank of Mount St. Helens. Pyroclastic flows moved over the lava towards the Kalama River Valley, ending with a dacite dome several hundred feet tall at the summit. Parts of this dome collapsed, spreading debris and shaping the southeastern wall by 1647. The volcano shows its power again, with new events shaping its history. The awakening of a giant in 1800. Mount St. Helens reached its highest point by 1647, showing a symmetrical shape. It then stayed dormant for 150 years until the Goat Rocks period began in 1800. This period started with a tephra date explosion, followed by andesitic lava flow, and ended with a date dome. The 1800 eruption was similar in size to the 1980 eruption, but it did not cause as much damage to the cone. Ash from this eruption drifted northeast over Washington, Idaho, and Montana. But the calm was misleading. Between 1831 and 1857, there were several minor eruptions, including a significant one in 1842. These eruptions likely came from a vent near Goat Rocks on the northeast side. The bulge that formed in 1980 was destroyed in the massive eruption of May 1st, 1980, which took out the entire north face in the top 1,300 feet of the mountain. In March 1980, Mount St. Helens had a big magnitude 4.2 earthquake, followed by steam emissions a week later. By late April, the mountain's north side started to bulge. On May 18th, a large 5.1 magnitude quake caused the north side to collapse. This triggered the largest rock and dirt avalanche ever recorded. Hot magma inside burst out in a massive explosion, devastating everything over about 230 square miles, and releasing a lot of sulfur dioxide gas into the air. This eruption was a major event, rated 5 on the eruption scale, and was a Plinian eruption, the most powerful type, where the north side fell, mixed with ice and snow, creating fast-moving mud flows. But there was still more to come. The intense volcanic activity of Mount St. Helens, which started with a massive eruption in 1980, became a key example of how nature can recover and bounce back. This eruption sent a staggering 3.9 billion cubic yards of debris into the nearby areas. Almost immediately, mud flows called lahars rushed into rivers, destroying bridges and tearing through forests. The ash cloud shot up between 12 and 16 miles above sea level, eventually traveling east across the United States and reaching as far as Edmonton, Alberta, by evening. The impact of the eruption was enormous, releasing 24 megatons of energy, creating a huge crater and reducing the mountain's height by about 1,300 feet. The aftermath was devastating. 57 people lost their lives, thousands of animals died, millions of fish were killed, and homes, roads, and railways were severely damaged. The catastrophe didn't end quickly. Mount St. Helens stayed active on and off until the mid-90s, with smaller explosions and new lava formations. But that wasn't the worst part. In the following years, particularly on October 11, 2004, new lava emerged, forming a dome that changed the mountain's landscape. This continued into 2005 and 2006, with temporary formations like a hardened magma structure called whaleback because of its shape. Although this structure eventually crumbled, the volcanic activity was still impressive, with a steam and ash column reaching up to 36,000 feet in March 2005, visible even from Seattle. As the dome changed, interesting features appeared, including a large slab that grew 6 feet per day. By mid-2006, this slab began to break apart, causing more rockfalls. Even though the dome kept growing, reaching 7,550 feet, it was still lower than its previous height before the whaleback collapse. After the chaos, new life and new stories begin at the mountain. Shaken ground. Mount St. Helens, unforeseen fury. On October 22, 2006, a 3.5 magnitude earthquake caused part of the dome to collapse, sending a 2,000-foot ash plume into the air. By December 2006, a large white steam cloud led to confusion, but experts confirmed it was a minor event. The volcanic activity that had been going on since 2004 created a significant dome within the crater, causing more seismic activity by January 2008. Although a large eruption seemed unlikely, the eruptions slowed down, and by July 10, 2008, the episode was declared over after more than 6 months of inactivity. The story of Mount St. Helens is particularly interesting to ecologists because of the idea of a biological legacy, the notion that life persists and adapts after major disruptions. This includes plants that survived the ashfall and the heavy flow of volcanic debris, as well as the organic matter and patterns in nature that were present before the eruption. These survivors played a key role in how the area has recovered, helping food chains to rebuild relatively quickly. While larger animals like mountain goats, deer, black bears, and cougars were severely affected, with many not surviving, the mountain goat population began to rebound, doubling by 2015. This ongoing recovery and the lessons learned from studying Mount St. Helens' eruptions offer valuable insights into how ecosystems respond to and recover from significant volcanic disturbances, showcasing nature's resilience and adaptability. In the Mount St. Helens area, many people have vanished without a trace. Since the big eruption in 1980, the mountain has attracted many adventurers. One of them was Lon, who went to the new summit to record the volcanic scenery on a VHS camera. Sadly, on his way back to Seattle, Lon died in a car accident with a bus. Miraculously, his camera survived the crash. In 2001, another incident happened when a man and his family hiked to the mountain's edge, taking many photos. As they were heading back, the man stopped to take one more photo from a high rock. When his family regrouped, they noticed he was missing. His children said they saw a strange man who looked like their dad, clapping loudly and making funny faces before he vanished. At first, they thought it was funny, but their father was never found, and search efforts failed. Terry, a vlogger, went on an adventure on Mount St. Helens with his team to make a documentary about nature's beauty. They filmed amazing landscapes across the Pacific Northwest. But things took a bad turn when disaster struck. As Terry climbed to the top, his rope broke, causing him to twist his ankle. Stranded at 8,400 feet with poor visibility and no way to communicate, Terry faced a huge challenge. He had to travel over 2 miles through dense forests with a throbbing ankle, testing his endurance. When they finally reached their camp, relief was short-lived. Nature unleashed a heavy downpour, flooding the only dirt road leading to the trailhead and making it impossible to pass. Terry was stuck for 2 days until the path cleared. But his problems didn't end there. Seeking medical help in Vancouver, Terry was misdiagnosed due to an X-ray error, which overlooked the severity of his foot injury. This mistake led to a severe infection, leaving him with a permanently disabled foot and a damaged lower leg, changing his life forever. But this wasn't the worst part. Despite his physical challenges, Terry's spirit stayed strong. He managed financial struggles and constant pain and eventually got a pension. This allowed him to fulfill his dream of owning a beautiful cabin in a serene landscape. Yet, fate dealt another cruel blow when his sanctuary was broken into, leaving him devastated and without his precious belongings, including essential equipment for his vlogs, a crushing blow that took away his passion and livelihood. Facing such hardships, Terry turned to online platforms to share his journey. The last post of his digital presence was a haunting image of an erupting Mount St. Helens, a symbolic goodbye to a chapter filled with trials and resilience. What do you think drove Terry to keep pushing forward despite these continuous setbacks? Let's discuss this in the comments below. Don't forget to like, share, and subscribe for more.